So this video is intended to wrap up our discussion of the concepts I started discussing today in today's lecture. Um, I s One of the points that we went through is the concept of evaporation, and we said that evaporation was this spontaneous process that all liquids undergo, and for that matter, so do solids to a lesser degree. That the particles in a liquid or a solid, even though they are relatively immobile, they do tend to move around and they slosh around. And at some point, because they're moving randomly, some of them will spontaneously break away from let me remember that. They do break away from the bulk of the liquid and they will evaporate into the gaseous state. And that's evaporation. And if you don't put a cap on it, if you don't restrict the particles from flying away from the liquid, eventually all the liquid will evaporate away. And that's driven by a push towards entropy. And as a natural result of the fact that particles are constantly in motion. And if you enclose the system in some way, those particles will come back. They will eventually condense back down into the liquid phase. They bounce off the walls of the container, come back and condense onto the liquid. And at some point, the rate of condensation and the rate of evaporation match up, and you set up a dynamic equilibrium. And then we argue that the pressure of the gas that you set up when you reach that dynamic equilibrium is what we call the vapor pressure of a particular liquid. Every liquid and every solid has a characteristic vapor pressure. So that's what evaporation is, but I didn't get to answer this last question, at least not in any detail that I was satisfied with. When does a liquid boil? What does it mean to... what does it mean for something to boil? Or what is characteristic about boiling? We say that boiling occurs when a liquid's vapor pressure is equal to the external pressure. So the idea being that you think of, this is how I think of it. I think of a liquid being having a vapor pressure. A pressure is like a force, it's force over area, and so the liquid is naturally trying to push itself away from itself. It pushes out into the surroundings, into the atmosphere. And at the same time, the atmosphere is pushing back down. There's an atmospheric pressure, there's an external pressure, and those two forces are in opposition to each other. Since usually we assume that the vapor pressure is lower than the external pressure wins out and keeps everything compacted together in a liquid. But if your vapor pressure increases, like it does with temperature, if your vapor pressure increases enough to completely exceed the external pressure, then the liquid will basically win out. It will win out that fight and push away the atmosphere and push its way out into the surroundings. So that's essentially what's going on when you boil something. When you boil something, you start producing these little bubbles. Those bubbles normally would be collapsed in by the external atmospheric pressure, because it's an opposition of forces. If the vapor pressure is lower than the external pressure, the external pressure will crush the bubbles, and in most cases they'll never form. Because the external pressure is too great. But if the pressure of the bubble, the vapor pressure of the liquid is greater than the external pressure, then that'll be enough to push away and oppose the external pressure. That's what happens when boiling occurs. Boiling occurs when all of a sudden the vapor pressure is high enough to completely push away and exceed the external pressure. So that actually has important consequences, because what it means is that the boiling temperature of a liquid actually depends upon the atmospheric pressure. It depends on the surrounding. A liquid has a different boiling point depending upon its ambient conditions. If you take something, let me give you an example of that, or let me show you how you can boil something at a lower a lower temperature than you might expect it to under normal atmospheric pressure. So let me get away from that and pull up a little video here. So I'll let the speaker explain what's going on here.
You can see I have some water, and it is only about 45 degrees. I'm going to put it into this vacuum pump. Suck the air out from above the warm water.
So yeah, he's going to suck the air out, and that's going to create a low pressure system above this liquid water. And what will happen? Even though the liquid is only at 45 degrees Celsius, well below its normal boiling point, normal being under normal atmospheric conditions, if we lower the pressure...
Whoa, my water's boiling at only 45 degrees or less.
Yeah. So again, the point being that all of a sudden it starts boiling rapidly. It all starts going into the vapor phase.
What starts?
You can see the steam start to build up there. And again, that is occurring because boiling occurs when the vapor pressure of a liquid is equal to or greater than the external pressure. If you drop the external pressure, something will boil at a lower temperature. So that is what boiling point, that's actually how we define boiling point. We define the boiling point as the condition when a substance's vapor pressure reaches the external pressure. Did I get a chance? So yeah, this is the chart that I was showing the other day, or showing in lecture today, is that if you change the external pressure, so normal ambient external pressures are at 100 kilopascals, or about 1 atmosphere. If a substance's vapor pressure increases enough to get up to that external pressure, then it'll boil. So again, water normally boils at 100 degrees Celsius. But I can do this. But if, say, I lower the pressure down to half of normal ambient conditions, then water will boil at a lower temperature. So in this case, a little above 80 degrees Celsius. So there's that. So to test your understanding, or to see if you can apply that understanding, I have a couple of questions or a couple of things to chew over for you. So here's one. I've heard it said that it takes longer to boil an egg at high altitude. So if you live in Colorado or something, you necessarily need to boil your eggs longer to cook them to a desirable consistency. Why might that be? So I would, spend some time, pause the video, think about this, and then I'll give you an explanation. Again, this is a conceptual question. People have asked me frequently, what types of questions will you put on an exam? Can we see more example calculations? You can speak to people who've taken my class before. I don't put an excessive number of calculation problems on my exams. I like a lot of conceptual questions. So this is an example of a conceptual question. Why would this take longer? How can we apply our understanding of things like vapor pressure, temperature, and whatnot to explain this observation? So at high elevation, here's my answer. So at high elevations, the atmospheric pressure is lower than at sea level. And as a result, the boiling point of water is decreased. So you might only be, when you're boiling water at high altitude, yes, it's boiling, but it's boiling at maybe only 90 degrees Celsius or only 85 degrees Celsius. And if you're cooking it at a lower temperature, it generally takes longer to cook things at low temperature than at high temperature. And that's the fundamental reason. Yeah, you are cooking the egg, you are cooking it, and you are boiling it, but that boiling point is much lower than 100 degrees Celsius. And so again, just to reiterate, since you're not cooking it at as high a temperature, the cooking process takes longer. So there's that. So that's one application of this concept of boiling point being pressure dependent. Here is another one, and this one is really wacky, or I think this one's kind of wacky. So yeah, here is another question. Let's see if we can explain this observation. So this fellow has taken a sample of water and he started boiling it. So he's going to bring it up. It's up to the boil. It's already, you can see it's already boiling already. What he's going to do is he's going to put a cap on it and then sort of pour cold water over it, and we'll see what happens.
Okay. Next thing is I'm going to take this rubber stopper here, and I'm going to turn the gas off and cap that so the solution starts to cool, or the water starts to cool. Turn the gas off, cap that. Okay, now this is the tricky part here. I'm going to move this over. I'm just move this whole thing into the sink here. And now I'm going to pour some cold water over this. I'll give it just a second here. And by pouring the cold water over it, I should be able to get it to boil again. See it boiling? Look at that.
That's pretty.
So everything you learned so far in my class, you had to add heat to get it to boil. Here I add cold water and it boils. See if you can figure that out.
So I don't know why he has to be a jerk about it, but yeah, let's see if we can figure that out, what's actually going on here. So the observation is somehow we're able to cause this liquid to continue boiling, even though in some sense it looks like we've cooled it down. So take a few minutes, take some time, think about this one, pause the video, show it to your roommates, show it to one of your friends, get puzzled about it, get confused by it, because it's an unusual observation. And I'll explain what's going on in just a second. So what occurs when so here's the explanation. We've said that boiling point depends upon an external pressure, a pressure opposing the liquid. So there is a pressure inside the Erlenmeyer flask here that's opposing the vapor pressure of the liquid. When he pours the cold water on the top of the Erlenmeyer flask, okay, that actually first he pours it on the top, and that cools down the gas inside the Erlenmeyer flask. So when you cool down the gas, you all know from the ideal gas law that if you cool down a gas, its pressure drops. So he's cooling down the entire system, but he cools down the gaseous part a little bit more quickly. So the pressure here drops very quickly. The vapor pressure of the liquid is still pretty darn high. And basically, the vapor pressure of the liquid becomes higher than the external pressure of this gas pocket. And when that happens, it starts boiling again. So let me say that again. The liquid has a vapor pressure. Its vapor pressure is determined by its temperature. Then there's a pressure up here which has its own characteristic temperature. So like the bottom of the flask is a little bit hotter than the top of the flask because he's poured cold water on the top of the flask. The bottom of the flask is still at a higher temperature. So the vapor pressure here ends up being higher than the external pressure from the gas pocket. And that difference in pressures is enough to cause the liquid to start boiling again. So again, that's another illustration of the idea that boiling occurs when external pressure and the vapor pressure of the liquid are equal to each other, or at least the vapor pressure of the liquid is higher. So again, I want to emphasize this again. We do think of vapor pressure as being a property of the condensed phase. It is a vapor, and it refers to a vapor, it refers to its tendency to go into the vapor phase. But it's a property of the liquid system, of the condensed phase, or in this case it could be, or not in this case, it's a liquid in this case, but it could be a solid. Solids themselves have finite vapor pressures, meaning that they do spontaneously boil away a tiny, tiny bit. Okay, so that's the end of this video. I hope this was educational. I hope you enjoyed this. I thought it was interesting. Yeah, I'll post this in a little bit, and I look forward to seeing everybody on Monday. Have a good weekend, folks.